We ready? I'm a fill-in. If you were expecting the other guy, I'm sorry, I don't know where he's at. But I'm going to talk about consequence-based cybersecurity. Does anybody in here work in a process plant? Nope? Yeah? Very good. So a couple things I talk about will be interesting and might actually pique you. If you want to throw stuff at me, go for it. This is how I started my career, writing these things. I actually built 2 submarines. I'm the plank owner on the USS Buffalo and the Chicago. That's actually the Chicago doing an emergency blow, and yes, it's an exciting ride. It's really awesome. Unfortunately, you got to join the Navy to take the ride. But I'm the CMO of a consulting engineering firm. I introduced myself because I am filling in. I'm the co-author of a book called Security PHA Review that'll be coming out from the ISA shortly. And I'm an industrial cybersecurity guy that has a massive amount of controls experience, starting with these guys, actually before this even, and a lot of years at Rockwell Automation and Honeywell, and building some, designing, architecting some high-end communication stuff. And then I'm actually a certified GICSP, if you know what that is. So the cool thing about submarines is, unfortunately, the ocean wants inside. This is actually pertinent. We're going to get to refineries in a snapshot. The weird thing about them is they sink in the ocean deliberately, and they're made out of steel, which is kind of odd. The pressure on the hull goes up 44 pounds per square inch for every 100 feet you dive. So if you think about that, the ship's not little. Most of them are about the length of a football field, give or take. Actually, most of them are a little bit longer than a football field, so 44 pounds per square inch for every 100 feet gets to be an awesome number really quick. You drive around blind, and most of the time you don't hit anything, and as you can see by the USS San Francisco behind me here, which was another LA-class submarine very close to the Buffalo's hull number, it actually accidentally hit an underground mountain, or an underwater mountain. Fortunately, they surfaced and drove home with very minimal casualties and damage, other than the fact that they wrecked the boat. It's packed with equipment that, quite frankly, virtually everything that's in containment inside of the submarine wants to kill you, including a rather substantial nuclear power plant that I ran. And so it's an interesting place to work, and if you dwell on it, it will absolutely drive you insane, and I've seen people actually lose their mind. As if that's not bad enough, the guy who's been on the boat the longest has been there for 3 years. Think about that. So when people talk about training, I'm always kind of surprised at the inability to face the fact that we need to train. And the military probably does it better than anybody on the planet because they turn over crews, especially in the Navy, on a regular basis. And obviously, if you get shot in combat, somebody's got to step into your shoes immediately. So training is a constant. There's a real good chance the guy sitting in the controls like you see right there, and you can see that's a pretty sophisticated video game he's got, with all the knobs and indicators. I never was on that boat. I tried to get on that boat. I really liked that boat. That was a USS Seawolf class. They didn't build a lot of them, but it was a state-of-the-art attack submarine, extremely stealthy, had some really cool technology. That guy's probably 18 years old that's driving the boat, with all that stuff in front of him. And the Navy trained him to do it. And fortunately, there's somebody sitting behind him watching him. But in reality, there's a really good chance the guy driving the boat, keeping you alive while you're sleeping, is 18 years old. Yeah, the nuclear operators are a little bit older, but our control room looks a lot like that too. So how does that compare to something like a refinery, for instance? So bad things can happen in a refinery. The advantage they have, and they do take advantage of this, is that they can run. If you've ever watched one of the CSB Chemical Safety Board's videos, or any of the other casualty videos that make the news or make it onto YouTube, they're pretty exciting when stuff goes wrong. And you do see people running rapidly, trying to stay alive. On a submarine, unfortunately, you can run from about here to the camera in the back of the room, and then you've got to turn around and go back and fight whatever you're running away from. Training's challenging in the civilian world because everybody wants to go home and play with their kids. They want to go home and have a life. But in the submarine world, you don't have much else to do, so you train constantly. The plant views fighting cybersecurity, unfortunately, a lot like fighting the ocean and the submarine world. So when I go into these places and talk to them, it's very common for them to look at me and say, Jim, I understand, but we've not had a cybersecurity problem, and I don't care. I'm much worried about it blowing up, or I'm much more worried about production. So it is a challenge to get their attention and to find a way to solve their problem. So, Brian, are you in the room? Yo? No. So the gentleman and I were in another country working at a refinery trying to do the work in their language. And it's a big oil refinery in Europe. And I was sent there early to figure out what their ISA 62443 zones and conduit structure should be, because they really had never even talked about cybersecurity before we showed up. I was there to figure out what their risk was. And these are common risk equations. In most of the world, risk is equal to probability times consequence. In the cybersecurity world, we tend to add a definition of probability where it's threat times vulnerability. Engineering and even plant management, even the guy who was the CEO of the refinery argued with us about the risk analysis. They argued specifically with me over dinner several nights. The guy reminded me that he was from a part of Europe that tended to stick people with long knives. It was an interesting conversation to have over dinner. But basically what he was saying is, you're not trying hard enough to figure out what my real risks are, and you're not getting it through. We don't believe you. That was a very difficult place to be in. So we sat and argued through this over and over and over again, and I tried to convince them that a hacker could actually cause the physical things that they were afraid of. And then I stepped back and I called in to the president of our company and I said, hey, can we talk a little bit about this challenge? And in the end, we decided we'd take a look at something called, something OSHA blesses and demands that companies do, called process safety management. And in process safety management, there's actually a standard/regulation, CFR 29. And it actually states, the part numbers up there, you can go read it. It's really great reading if you want to go to sleep tonight. But it actually defines how they're supposed to manage this. I'll summarize it for you. Basically, don't let the bad chemicals out, whatever they are. So keep them in containment, period. It requires a very systematic approach to a lot of things, and it also requires that they periodically do something called a PHA. And the most common method that people use today in wet industries anyway is something called a HAZOP. And up here, you'll actually see a P and ID drawing, and beside it, what a HAZOP typically looks like, that's done at least in computer software, which most of them are recorded in today. So they mark up the P and ID drawings, they do a HAZOP. And I sat back and went, well, this might work, so let's take a look at those. So we asked the refiner for their HAZOPs. Their HAZOPs were dated 1960-something. They weren't in the United States, so they weren't required to do them on a regular basis, but it was a starting point. We sat down and started looking through them, and we started asking ourselves some questions. But before I get to that, let's talk about what a HAZOP does. So what a HAZOP does is it's designed to put the really smart people in the room around a table to talk about the process, node by node in the system, and they look at every single possible scenario and what the consequence of that scenario is. So what they're trying to determine is what's going to blow up, basically, what's going to catch on fire, what could leak. If it does leak, what will happen? And then they're trying to find a way and make recommendations for how to prevent those things from happening. So you hear defense in depth strategy in the process industry, they talk about layers of protection. So they'll start talking about layers of protection and looking for ways to solve things. So this is a very rigorous methodology. What you see here is one that was actually marked up by us as an example, but it is a very common, and I'll go into it in more detail in a minute. So as a result of doing this and talking to the customer and getting the customer's buy-in, and by the way, when we admitted to the customer that we agreed that the risks that they had already calculated were the risk for their facility and were the risk for individual parts of their facility, then they said, okay, we agree. That we can buy into. And all of a sudden now we had a group of people, including engineering, that said, yeah, we need to do something to prevent those things from happening. Out of that, and as a result of that, the president of Connexus, Ed Marzell, and myself decided that we would write a book. And so we wrote a book on a topic called Security PHA Review, and we developed this. The really cool thing about it, it's been peer reviewed by some of the people in the room, I suspect. It actually complies with the ISA and the IEC standards, both for process safety, functional safety, if you're familiar with that term, as well as for the industrial cybersecurity standards. The industrial cybersecurity standard is listed there in the ABCDE thing. So it's actually designed to help you do those things and make those decisions. The net result of this is for any hackable or significant consequence, it actually makes a recommendation of either a security level or a non-hackable solution. I know that's not good English, but a non-hackable solution is something as benign as an analog circuit. If you pay attention to the United States government, you'll notice that the Senate just passed down a bill called S79 that talks about analog and the electrical grid, possibly. So a HAZOP, I'm not going to go into how to do these, but in essence, it's a very structured effort. And the net result is we know what deviations in every node now ideally will actually cause a problem in the facility, and we look for ways to actually reduce the likelihood of that event happening. So how a Spur differs is once a HAZOP's done, I don't go back and do a HAZOP. My company does HAZOPs for companies, and I really don't want to be in that business. I sat through one once and decided I never wanted to do it again. I'm a physicist by education, so I found that to be very painful. But man, that is hard to read. I thought that was actually my eyes. What we do is we sit down and we look at the causes and we look at the safeguards. So what we're looking for in a HAZOP is something is going to make it happen. You're going to shut off a pump. You're going to open a valve. Temperature is going to go high. Something is going to make it happen. We look at all the causes to see if any of them are hackable. And then if the causes are not hackable, then we move on. If the cause is hackable, then we look at the safeguards. If the safeguards are hackable, then we got a problem. We actually have a hackable consequence. We have something that could actually realistically happen if some smart person figures out how to get in and make a mess of the system, or somebody who has a grudge against the company. So you guys drove here today, walked here across intersections and stuff like that. Do you know that every intersection you cross, somebody actually did a calculation like this to decide how many people die at that intersection every year? Pretty comforting when you think about it, right? Airports, planes, cars, everything, traffic lights, they're all designed with consequence tables. Risk, all right? So what we did was we added a column to the right, which is security level. This is normally done well in advance of ever doing anything, right? So the reason you do that, and it's an executive level decision, you don't get to decide what the risk is, and you don't get to decide what risk your company is willing to accept unless you own the company, all right? So the board is going to make that decision. Its executives are going to decide what risk the company can tolerate. The reason why there is a risk, unlike the United States Navy, the Navy has risk. I mean, they sink boats in the ocean deliberately with nuclear power plants and weapons in them. It's a brilliant idea. But they can actually spend money that the civilians can't to do stuff because they're spending government money. So the net result is, in the civilian world, we have to make decisions and decide how many people we're willing to get hurt. And normally that risk falls right in the middle there where it says typical risk tolerance is about 1 in 10,000. You'll hear that related a bunch of different ways, like 10 to the minus fourth you'll hear a lot, or e to the minus fourth or something like that. It's actually a 0.0001 chance, if you want to do the math. So 1 meaning it's going to happen, a fraction of that meaning you've got some odds. And so we added the security level column, and here's where it gets really interesting. You have to decide. Everybody familiar with the ISA 62443 cybersecurity standards for security level, right? You have to decide what security level you want to take on for what risk, right? It's a hard decision. The difference between security level 2 and security level 3 is a boatload of money everywhere. Security level 4 probably isn't achievable today yet. So just to give you an idea how difficult security levels are. So you don't do this at random, you don't do it in the dark, it actually takes some thought. Here's what the process really looks like. I'm not going to go into this, it's painful. It's not hard to do in practice, But in reality, what happens is when you get over here to where it says choose recommended security level from the safety consequence table, that has to be done before you ever choose. If it isn't done before you choose, then you're going to sit and argue about this for a week too. And in reality, the people in that room can't make that decision. The board has to make that decision. All right. So the net result of this is if the consequences are hackable and the safeguards are hackable, then the consequence can be generated by a hack. All right? Whether it's intentional or accidental or whatever, it can be generated by a hack. So it makes sense. The question you have to ask then is the consequence significant enough that I'm going to spend money to protect against it? That sounds terrible, but think about every intersection. I could make an intersection safe so nobody would ever die in it. And you would kill me because you would hate using it. How many cars get to go through an intersection where nobody dies, right? Not very many, and not very fast, and not very often. So the challenge is, where's the balance? Where's that line at? So let's look at a quick scenario. So this is called a continuous stir batch reactor. The first time I ever saw these, I was right out of the Navy, and I got hauled into a plant in Barberton, Ohio, and I had sold the guy a variable speed drive to run that cooling water pump. Variable speed drives back then, this is like 1988, variable speed drives weren't very well known and very reliable at that point. And the thing kept shutting off, and every time it shut off, a whole bunch of bad things happened. As a matter of fact, what happens in this case is the temperature starts climbing, and a safety system engages, and it opens that valve on the bottom of that big batch reactor, and it dumps a whole bunch of really nasty chemicals that are in the process of going exothermic into a giant vat of water, really nasty water. So you have a steam explosion, all kinds of cool things happen. So I went out to the facility, and they had turned on this system, and I was standing there, and I noticed the lights dimmed. And I'm like, well, that's interesting, man, the lights in the building. And then alarms started going off, and I'm still standing there looking at the lights, wondering why the lights in the building dimmed. It's a large facility. And my host tackled me, knocked me behind an explosion wall, a physical barrier. And then there was a really loud noise, and what had happened was the drive had shut off, and this valve had opened, and all this stuff hit the water. It did exactly what it's supposed to do, because technically that's a safe thing. However, when it does happen, people hide because it's nasty. If it didn't do that, the batch reactor would explode. It's only a matter of time until it does. These are used all over the world all the time. It's amazing how many things are made this way, and so now you know how it works. There's a simple safety circuit here that measures temperature on the TZT403, the logic circuit there, which is actually coming from a PLC or a safety instrumented system, tells that valve to dump, and it actually is a valve that's forced close, and so it automatically opens if for some reason the control signal isn't there. So in the Spur analysis, what we do is we look at the cause over here on this side. We ask the cause, can that actually happen? And you can't read the cause. I probably can't read it either from here. But basically, the water pump shuts off for some reason. And when it shuts off, the cooling jacket doesn't work, and the reactor starts getting much hotter. So we looked at that and said, what controls the pump? It appears unlikely that a cyber attack, in this case, could actually cause the pump to break or fail. However, the start and stop functionalities in a PLC. Sounds normal, right? So automatically we go, well, the cause could be created by somebody shutting off the pump or some moron selling them a variable speed drive to run the pump. That's a joke, sorry. All right, so then we look at the safeguards themselves. So the safeguards are listed here. By the way, you can do these for everything. So in the electrical world, you could do it to protect assets. In an environmental space, you can do it to protect the environment. In a lot of these companies, you do all that. You protect people, you protect assets, you protect the environment, production, you name it. All those things are taken into account. So in this case, there's a safety instrumented system that actually is designed to open that valve. However, the SIF is actually in an SIS, and what did we learn last Christmas about SIS systems? They are hackable and have been attacked. All right, so the net result of that is the cause or the safeguard itself can be attacked too. So we look at that and we say, that's not good. What's the consequence? Well, if you read down through the consequence, which I apologize, it's a little out of focus, potential fire, potential vapor cloud explosion, potential single fatality if the operator's expected to be in the area doing maintenance or anything like that. So basically, you could kill somebody. So if you can kill somebody, that's that 10 to the minus 4 thing, and you're required to implement security level 2. The problem with security level 2 is, in the case of the refinery, the problem with security level 2 was they didn't have any security, and they all wore USB sticks around their neck walking around the facility. They didn't lock the doors, and they couldn't even shut the blast door on their control room. Bad. So the net result of all that was we took a step back, and they said, is there another way? And so we took a look at it and said, let's take a look. And so we found another way. We actually implemented a relatively simple solution to solve the problem. We did something with an analog mimic. So what we did in this case is we actually designed an analog circuit around the SIS system, and the decision now is actually being made in that device instead of that one only. So if the PLC says, or the SIS system says to this device, hey, you need to open up and let that valve go, it goes. If the analog circuit says the same thing, it goes. So basically putting them in parallel, now I'm not totally dependent upon it. Is this an expensive solution? It took a little bit of engineering to put it in, but in reality, it was much cheaper than going to security level 2 in this part of the process. So those are challenges that we face trying to solve these problems. So here's a really cool thing. It's amazing. Years ago, we did a presentation here where we talked about a distillation column on stage, and I put a very junior chemical engineer on stage, and Brian Singer was hacking the distillation column, and the chemical engineer was describing how it would react. We designed all these process plants, if they're designed correctly. They're actually designed, for the most part, to protect themselves when the process goes awry, for the most part. That's not a perfect answer. However, it's amazing how many times a really complicated security problem, if you take a step back, if you look at the HAZOP, for instance, or whatever risk analysis they've done, if you take a look at that, you might be able to figure out how to use an alternative method to solve the cybersecurity problem, something like a pressure relief valve and a spring. Maybe you don't hook up the motor overload switch to the PLC with a digital connection. Maybe you actually use relays. Somebody was up here earlier talking about building automation. You know, the cool thing in the fire code, a building automation system is not allowed to talk directly to the fire control panel. The fire control panel is not allowed to talk digitally or directly to the building automation system. They're patched together with a mechanical relay. Think about that, all right? So we can do some cool stuff. SPR benefits, not changing the risk that you already figured out. So one of the challenges we have in this industry when we're doing vulnerability assessments and stuff, or we're doing any level of cybersecurity work for them, is how do you tell them what their risk is, right? Well, first of all, you trying to tell them what their risk is probably isn't going to be taken very seriously unless you really have some intense bona fides. I'm a physicist, and they challenge me, right? So it's a little bit of a challenge. Looking at the actual cause and the safeguards for vulnerabilities is pretty easy to do in reality. Whipping through a HAZOP with guys who actually know how to read these things and know how to read the P&ID drawings isn't that painful. It actually can be done pretty quickly. It gives people a thing to focus on. So think about it from a strategic position. If you're trying to figure out how and where to start, and you run something like a refinery and one of us walks in and says, hey, I'm a cybersecurity dude, I'm here to help you. And they're like, yeah, get out. Okay, wait a minute, we can't say that to you because the boss said we need to do cybersecurity, so what do you got? And you start talking, the challenge we run is, one, we don't always understand their language. Number two, they got a whole bunch of other things on their mind. So if we can find a way to make this easier for them, to start to help them, to give them a path, to actually make sure that the really bad things that they're the most afraid of won't happen, then we can take a step back and actually do the other things too. So it works pretty well. Actually, it works really well. Fits right in with the standards that exist. The pictures you saw up there, in full disclosure, is actually my company's product called Open PHA. It's really expensive. It's on the internet, on connexus.com. It's free. I'm not kidding. It's actually free. So you can actually do this work for a customer You can actually pull in their HAZOPs and do the work for them in the tool, no cost. There'll never be a cost. We give away the basic version of Open PHA at no cost. And here's a really cool thing. It runs on Windows, Linux, and Mac, and I run it on a Mac. And then there's a fancier version. That's me. Questions? Questions? That's for the back.
We have a question here.
Oh, no, that guy can't ask any questions. He reviewed the book.
Thanks, Samuel.
Hey, that's Jim. Pretty cool. I actually hit 0.00 on the clock down here. That's awesome.
Okay, sure. Hi, I'm Andy Bachman from INL. Jim and I know each other. It always seems to me like it had to be a terrible idea for safety instrumented systems to become digital, and then still worse for them to integrate for convenience and efficiency into control systems. One big digital playground. What happens when you guys go and see a setup like that? What do you start to think, and what do you start to recommend?
That's a good question. Did everybody hear the question okay? All right. We don't panic. How many hackable events, how many clearly defined hackable events have been documented in industrial applications? Seriously. I know we can hack building automation systems day and night. I used to be the vice president of Tritium, so all you guys who know what Tritium is in the Niagara framework, that was me. Now you know why I'm at Connexus. I'm kidding, it's a joke. The reality is that it is a point of concern. However, it doesn't scare me to death. There are some things that vendors are doing that make me nervous. The vendors that are making the SIS system look just like the PLC and putting it in the same chassis with the PLC, I don't think that's wise. The vendors that are recommending that the PLC and the SIS system live on the same network, I don't think that's wise. I think segmentation is still a necessity. It is going to be pretty much an automatic conversation about this. Once we see an SIS system and it's connected to stuff, we're going to automatically assume that something could get on the network and get to it, even if it's just somebody with a laptop that comes in from a vendor could accidentally install malware that affects the SIS system. We've never heard that happen before. Does that answer your question?
No, but thank you.
No, but thank you.
Any other question? Yeah.
I want to thank all you guys for sticking around. That's pretty cool.
Hi, good afternoon. Paul Petrosky from Royal Dutch Shell. The new safety standard from IEC requires a cybersecurity risk assessment to be performed on safety systems.
Yeah.
Have you done that? Do you have any experience with that? Because we're trying to get our feet wet in that area.
Yeah, we do every level of risk assessment that ever existed. So we just did a risk assessment on a control system for Fertile. Everybody know what Fertile is? No? So sometime in the next 4 or 5 years, they're going to light off a giant fusion reactor in France called Fertile. I suggest you be on the other side of the planet just in case they bend the Earth. I'm just kidding. I'm kidding. I promise you. It's a bad nuclear physics joke. I apologize. But, you know, you got to look at that stuff, right? So here's the challenge with risk analysis. You know, a lot of people, even including myself at one point, who thought that I should do risk analysis on the network devices themselves and the network topology. And the reality is, there's always going to be flaws in the network devices, right? When's the last time a US cert dump didn't include like every Cisco switch on Earth? You know, it is very uncommon to get almost every week 30 or 40 Windows or 30 or 40 Cisco or 30 or 40 Juniper or whatever it is. You need to patch this, there's a new vulnerability. If you're trying to run a refinery, you know what they do? They shut that stuff off. They just can't think about it. It's hard enough just to get the job done, right? They're doing HAZOPs, they're doing maintenance constantly, they're fixing things. They just got to keep the plant operating because that's how that's what their job's based on. So when somebody comes in and says, I want to do a risk analysis on your network, yeah, that's viable. You know, when you do a real risk analysis on Wi-Fi versus wired, you know what you find out? Wi-Fi is probably more reliable than wired. It doesn't feel right, does it? But that's what happens when you do the real risk analysis. So in that case, yeah, I would do the risk analysis, but it's only part of the picture. You have to measure it as part of the overall problem. I'm not recommending that you not do digital stuff. I'm a digital guy. I love zeros and ones. I know how to hack Modbus. I know how BACNet's built, how the protocol works. I know how PHA. If you go on my profile on LinkedIn, you'll find out the one guy who ever said I knew what I was doing is the guy who still runs the OPC Foundation. There's nothing wrong with doing it. It just isn't the panacea. Just like getting the stamp that Dale talked about earlier, if you get the cyber hygiene stamp, that stamp really only tells you a little bit. It doesn't tell you enough to get you out of trouble. Fair enough? We can talk at length about risk analysis, though.
Any other question? I will do one more. As Andy will not do that question, I will like to ask you how security PHA is aligned or supports CCE.
Start over again.
Okay.
I moved here to speak.
Basically, the question is how security PHA supports or is aligned to CCE, to consequences-driven cyber-informed engineering.
Is that what you're doing?
Probably yes.
They're very similar. My process, this process that we're defining here is one way to do consequence-based cybersecurity. It's not the only way to do consequence-based cybersecurity. It just happens to take huge advantage of the fact that somebody's done HAZOPs already. If you haven't done HAZOPs yet, then you get to flip a coin and make a decision about which way you're going to go and what you're going to do. But if you already got the HAZOPs done, man, this is a fast way to figure out what you need to focus on now.